This is a sequel video to my earlier videos on the RSA encryption algorithm, proof of RSA encryption. So before I get started here, I'll just let you know that I'll be assuming that you're pretty familiar with the RSA encryption algorithm, and if you're not, then go ahead and check out my earlier series on the mechanics of RSA encryption. Okay, so the proof of correctness of RSA encryption is one of my very favorite things to talk about. I had been searching for an easy way to prove RSA for about 2 years when I finally came up with a way a couple of months ago. This proof is pretty similar to what you'll find on Wikipedia, but I think that this is probably much easier to understand. So you'll recall that the way to encrypt a message in RSA encryption is by plugging in a secret integer message m into the expression m to the e power mod n, where e and n are those public key values that you're going to use to encrypt your secret message m. And whatever m to the e power mod n turns out to be, we call C for ciphertext or encrypted message. And you'll recall that the way that you decrypt messages in RSA is by plugging in that ciphertext message C into the expression C to the d power mod n, where n is that public key value and d is our private key value that we're going to use to decrypt C. Now, this expression c to the d power mod n should equal our original integer message m. But why does this work? That is, why does c, which is equivalent to m to the e power mod n, all raised to the d power mod n, equal that original integer message m? Well, to answer that question, we have to know two things. 1. A modular arithmetic exponentiation law. And 2. Eulers theorem. In some proofs of RSA encryption, and in fact in the one that Ron Rivest, Adi Shamir, and Leonard Edelman used, they used Fermat's theorem, but I just think that Euler's theorem is easier to understand. So first off, this modular arithmetic exponentiation law tells us that when a, k, and n are positive integers and a is less than n, then a to the k power mod n is equal to a mod n, all raised to the k power mod n. So quick side note here, the n does not necessarily have to be the semi-prime number n that's used in RSA encryption. The only restrictions in this law are that a, k, and n are positive integers and that a is less than n. So why is this true? So this is true because if a is less than n, then a mod n simply equals a. And why is this true then? Well, if you divide n into a, and a is less than n, then n is going to divide into a 0 times because it's larger than a. So when you multiply n by 0, you're going to get 0, and a minus 0 is simply a. So the remainder of a divided by n is simply a when a is less than n. So if we know that a mod n is equivalent to a, then we can substitute a mod n in for a in this expression here, so that we get the equation that reads a to the k power mod n is equal to a to the k power mod n. And these two expressions are exactly equivalent when a is less than n. Therefore, we've proved that a to the k power mod n is exactly equivalent to a mod n to the k power mod n when a is less than n. Okay, so that's the first part of our proof. Now the second bit of information that we need for our proof is Eulers' theorem. You might recall that in one of my earlier videos I said that the expression that the key generator uses to generate the value of the decryption key D is E times D mod n is equal to 1. So for example, if E is 7 and n is 3,233, then we know that our equation is 7D mod 3,233 is equal to 1. Sorry, I meant phi n. So the phi of 3,233 would be 3,120. So E times D mod phi n is equal to 1 is the equation that the key generator will use to generate the value of the decryption key D. So 7D mod 3,120 is equal to 1. So to solve for D, we know that 7D has to be some multiple of 3,120 plus 1. So for example, if we let x equal 1 here, then we know that 7D has to equal 3,120 times 1, which is simply 3,120, plus 1, so 3,121. And in this case, D is equal to 445.857143, and so on. But the important thing to take away here is that when x is 1, D is a decimal. So what we can do here is keep on changing this value of x and setting it equal to increasing integers until D is not equal to a decimal, that is, until D is equal to an integer. And it turns out that this happens when x is 4 in this specific instance. So 3,120 times 4 is 12,480, and that plus 1 is 12,481, so 7D is equal to 12,481. And in that instance, D does equal an integer. D equals 1,783. So in this particular instance, 4 worked as our x, and that was because 12,481 mod 3,120 is equal to 1. And this, when we set 7D equal to 12,481, we got that D was an integer. So the neat thing is that we can make this idea that we used to solve for D as an integer, we can make that generic, and we can make that apply to this whole equation E times D mod phi n is equal to 1 when we're trying to solve for D. We can say that E times D is equal to phi n times some integer that we don't know, x, plus 1. And this is essentially saying that E times D is some multiple of phi n plus 1. So that bit of information is pretty important, so keep that in mind while I'm explaining Eulers' theorem. So Eulers' theorem states that when a and n are coprime positive integers, phi n is Eulers' totient, and x is a positive integer, then a to the phi n times x power mod n is equal to 1. Now, these values aren't necessarily the ones that I was referring to when I was explaining the modular arithmetic exponentiation law. All the restrictions that these variables have to have are that a and n are coprime positive integers, phi n is Eulers' totient, and x is simply has to be a positive integer for this expression or equation a to the phi n times x power mod n is equal to 1 to be true. So I unfortunately do not have a proof for Eulers' theorem yet. It's a lot trickier to prove than that modular arithmetic exponentiation law that I was explaining earlier, so we're just going to have to take Euler's word for this in the meantime. Okay, so let's recap. We proved that when a, k, and n are positive integers and a is less than n, then a to the k power mod n is equal to a mod n all raised to the k power mod n. And we also said that when a and n are coprime positive integers, phi n is Euler's totient and x is a positive integer, then a to the phi n times x power mod n is equal to 1. So now we're going to use these two bits of information to prove what we originally set out to prove, and that is that m to the e power mod n all raised to the d power mod n is equal to m. Okay, so what we're first going to try to do is simplify this expression, m to the e power mod n all raised to the d power mod n, to m. But first, one quick note. I think I may have mentioned in my earlier videos, but m has the restriction that it must be less than n and coprime to n. Okay, so the first thing that we can do is set m to the e power mod n all raised to the d power mod n. We can simplify that to m to the e d power mod n. And this is because of the modular arithmetic exponentiation law, which tells us that a to the k power mod n is equal to a mod n all raised to the k power mod n. So you see here that we have this expression m to the e power mod n all raised to the d power mod n. And that's, I'm relating back to this, a mod n all raised to the k power mod n. So essentially what I'm doing here is treating a as m to the e power, n as n, k as d, and then again n as n. So the modular arithmetic exponentiation law tells us that m to the e power mod n all raised to the d power mod n must equal m to the e d power mod n. So you notice that for this to work, m to the e power, which we said was like a, has to be less than n, that semi-prime number in RSA encryption. Okay, so what can we do after this? Well, I explained earlier that in RSA encryption, e times d is equal to phi n times some positive integer x plus 1. So what we can do is substitute in phi n times x plus 1. We can substitute that in for e times d here. So that means that m to the e times d power mod n is equivalent to m to the phi n times x plus 1 power mod n. And that's because of how d is calculated in RSA encryption. Okay, and from our days in algebra, we know that some number x squared times x cubed is equal to x squared or x to the 2 plus 3 power, or simply x to the 5th power. We can use that same principle here. We can set m to the phi n times x, or m to the power of phi n times x plus 1 to m to the 1st power times m to the phi n times x power, and we know that that's going to be the exact same thing as m to the phi n times x plus 1 power. So this is because of the properties of exponents. Now, Euler's theorem told us that when a and n are coprime positive integers, phi n is Euler's totient and x is a positive integer, then a to the phi n times x power mod n is equal to 1. So we have that exact same thing right over here. We have m to the phi n times x power mod n. Euler's theorem says that we can simply simplify that to 1. So now we have m to the first power times 1, and that's because of Euler's theorem. And m to the first power times 1 is, of course, simply m. So that's it. We have proved what we set out to prove. We have proved that m to the e power mod n, all raised to the d power mod n, we have proved that that equals m. So what we've done is proved that encryption and decryption works. So that about sums it up for this video, and thank you for listening.